Hi everyone, welcome back to the video on thermochemistry and thermodynamics in prep for Chem Olympiad. Right, so for this particular video, I'll be going in depth into quite a number of other types of enthalpy changes. But in particular, I might want to spend a bit more time focusing on some that is quite relevant still for your chemistry O-level syllabus. So that at least when you look at some of these concepts, right, you kind of have an idea of if O-level ever tests you on any form of database question with regards to thermodynamics or thermochemistry, chances are some of these concepts may come out, and at least you kind of have a heads up in terms of the possible things that you may be required to analyze the data on for even for O-level itself, right? So let's get started first with the first type of energy. So in total, I'll be talking about quite a number of different types of energy for this whole video, which will take a while. But specifically, I just want to first highlight that I will be spending quite a bit of time talking about ionization energy, electron affinity, as well as the concept of lattice energy. So these three in particular, you realize that they do have quite a lot of relevance to the current chapters in the O-level syllabus, especially on this chapter called atomic structure. So atomic structure is something that you learn in Sec 3, something that doesn't seem to be very important at all because it's just about protons, neutrons, and electrons, right? But you realize that when you go into this whole idea of enthalpy change, actually there's a lot more that they can actually test you on with regards to the chapter on atomic structure. I'll also be talking about a bit about bond energy because there is still some relevance to the kind of calculation questions at O-level when it comes to energy changes. So bond energy, right? So similar to what you have learned currently in O-level, right? Bond energy refers to the energy required to break a specific covalent bond in a particular molecule. Just that when you look at this A-level definition, right, you realize that the additional information that we want to look at here is about molarity and also about the state. So they're actually looking at the molecule in the gaseous state and how do we then break that covalent bond itself, right? So because breaking of bonds, just like what you learn now in O-level, right, bond breaking, right? Bond breaking is the concept-wise, just think of you trying to break a chopstick, right? So you must always put in energy for that process to happen, and therefore this is always going to be an endothermic process. Okay, so bond breaking is going to be endothermic because energy is required to break something. The opposite will be true then, because when you look at bond forming, then you are looking at energy being released, and therefore this is an exothermic reaction. So when you look at a particular bond, depending on whether you are breaking it or whether you are forming it, it's just a matter of whether it's exo or endothermic. The magnitude or the value itself will be the same. Okay, so that's just something for you to think of. And of course, we know that the stronger a bond is, the greater the bond energy will be, right? So you need more energy to either break or to form it. So we just use this as an example here, right? So over here I have a molecule of methane, right, CH4. So in total there's actually 4 sets of these C single bond H covalent bonds over there, right? So since they are all the same type of bonds, single bonds between carbon and hydrogen, I will expect the bond energy for each of these bonds to be equivalent, right? So something for you to take note of. So we are going to take a look at this in a few examples. So in A-level itself, right, what will also become like a Bible for a lot of you here is this idea of a data booklet, right? So we don't have this in our O-level syllabus because we don't really need to go so in-depth into all these various data and energy values, etc. But in A-level itself, you'll be doing a lot of calculation in terms of enthalpy change, etc. So there's actually a few pages of this bond energies that's available over there for you to do the calculation. But in O-level, what will happen is that if we require you to calculate any form of bond breaking or bond forming process, we will actually give you the data itself, so that you can actually apply this to calculate the value, right? So if you look at the first example here, over here, what this tells us is that the bond energy for a HH single covalent bond is 436 kilojoules per mole. So if you use 436 kilojoules per mole of energy, you can actually break up the H2 molecule into 2 sets of hydrogen in gaseous state, right? So remember about the definition. So the second one over here is the bond energy for HCl is 431. That means to break up one molecule of the HCl into the individual atoms, and the energy involved is 431. Yeah, so that's the whole idea of bond energy, right? So similar to what you have learned in currently in O-level, we know that the overall reaction would involve bond breaking and it also involves bond forming, right? So there's a way to calculate enthalpy change by actually adding up all the bonds that's been broken and also adding up all the bonds that's been formed to see how it works out. Okay, but take note that sometimes these calculations, right, there can be discrepancy, like what I said earlier in the previous video, because there's always difference between theoretical as well as experimental values. Okay, so we can use one example here to see how do you actually apply this whole concept, and it's also a revision for O-level and the possible questions that might come out. So over here, there's this reaction here. You have a chemical here with the formula of C2H2 reacting with oxygen to form CO2 and H2O. So the question requires you to use the bond energy from the data booklet to calculate the enthalpy change, right? But over here, my focus is not so much about data booklet. I'm more concerned about whether you understand the method to do so. So how do you go about doing this particular question? First and foremost, we need to have an understanding of the type of bonds that we're looking at. So for oxygen, so we are going to backtrack a bit to your chemical bonding chapter. We need to know that oxygen actually exists as this kind of molecule, where there's a double bond first. Likewise, we need to know that carbon dioxide actually exists as this kind of molecule, whereby C double bonded to a O and also C double bonded to another O. We also need to know that water is essentially a bond between hydrogen, single bond to oxygen, then another single bond to another hydrogen. So for this first chemical that's over here, C2H2, right, in case you are not too sure how it looks like, you may eventually come across this when you learn about organic chem, but let me just put it out here first for you, right? So now that you have a clearer idea about the kind of structure formula, right? These are what we call structure formula. It shows us the bonds that's present within the molecules. That's where we can start calculating our bond breaking and bond forming process. So in every reaction, there's always going to be bond breaking, right? So bond breaking happens at the reactant, and then there's always going to be bond forming, and that happens as the product are being formed, right? So what we can do here is to actually just add up the amount of bond energy depending on what kind of bonds we are looking at. So let's take a look at the left hand side first for the reactant. So what are the bonds that we need to break? We definitely need to break the bond between H and C, the single bond. We also need to break the bond between C and the triple bond to another C. We also need to break another set of bond between the H and the C, right? Because in total there will be these 3 sets of bonds, right? And what's more important is to know that the equation tells us that there is 2 sets of the C2H2, which means that all these bonds that's been broken is actually 2 sets of it. Now, what else do we need to break over here? There's also the oxygen, right? So oxygen, we know that we need to break this O double bond O bond, and the coefficient of 5 here tells us that we are looking at 5 sets of this that needs to be broken. Right, so when you add up these 2 sets of energy, depending on what the values are, and multiply it by the specific sets, right, you will end up with the energy that you need for bond breaking. Okay, so bond forming, we are looking at the formation of a C double bond O and a C double bond O over here based on CO2, right, and this we need 4 sets of it. And then we will need a H single bond O as well as a H single bond O, and this one we will need 2 sets of it, right? So what this shows you is that when we add up all the bond energy value, right, we will actually be able to determine how much exactly do I need to break bonds, right? When I say need, I'm referring to the process of endothermic, because I know that bond breaking is endothermic process. When I talk about bond forming, I know that it's going to be exothermic. So how much do I need to release to form all this energy, right? So arbitrary, let's give it just an algebra so that we can use it for our calculation. Let's say that bond breaking is a value of A, right? What exactly is A doesn't really matter, and bond forming is a value of B, right? So when you calculate bond breaking and bond forming, right, you need to know that you are just adding up the values of the bond energy. So you also need to apply this idea of whether it's endo or exothermic, so you can help yourself look at it as a vector, so that you look at the unit, the quantity, as a form of whether there's a plus sign or there's a negative sign, right? So we know that bond forming is exo, so the symbol over here for this amount of energy must be a negative, right? So because that in itself is the whole idea of exothermic. And then for the bond breaking, this must be a positive value because it's endothermic, right? So now when you have these 2 sets coming together, that's where you can apply your formula, which you have already learned in your current O-level syllabus. If not, you can apply the Hess law, right? It's the Born-Haber cycle. So same thing over here, what we will end up with, we'll end up with A with a summation of B, provided that B we know that it's a negative value because exothermic, and then A we know that it's a positive value. Right, so I think this is something that you need to think of it yourself, because the last thing you want to do is that you have calculated everything, but you forgot about the kind of energy change, whether it's positive or negative, and you just add them up, right? And then you would not be able to address the enthalpy change, right? So that is something for you to take note of. Okay, so the next energy I want to talk about now is enthalpy change of atomization. Now, atomization just refers to energy change required when you're forming one more of gaseous atoms from the elements. Right, I won't be going into too much details over here. You can look through the notes yourself. Right, and you can try out some of the questions using the slides too. Like what I mentioned at the start, I want to focus on this idea of lattice energy, ionization energy, as well as electron affinity. So let's first start with this whole idea of lattice energy. Now, lattice, right, you will recall that you have learned about this before in your ionic compound chapters, the structure of the chemical. So lattice energy essentially refers to the heat that's evolved when one mole of solid ionic compound is formed from its constituent gaseous ions. So be mindful about the kind of conditions that we're looking at, and we're looking at gaseous ions. So what this means is that we are looking at ions coming together, and this is when there's this idea of electrostatic forces of attraction being formed. Right? So when there's an attraction being formed, just like when there's a bond being formed, the energy change must be exothermic, because two ions are coming together, they're forming attraction, energy must be released in order for that to happen. Right? And this is actually an indication of how strong the type of ionic bonds we are looking at. Now, the stronger the ionic bond, the more exothermic the kind of lattice energy we are looking at, because the attraction form is so strong, right? That so much energy is being released out when that happens. So lattice energy actually depends on something that we call charge density. We look at the charges of the ions as well as the sizes of the ions. Now, how does this help us in terms of our current content, in terms of the concept? You will recall in your in the whole process of learning about ionic bonding, in your workbook or in your test series, you may have come across questions whereby you are being forced to compare about, for example, an ionic compound like sodium chloride versus an ionic compound like magnesium oxide. Compare in terms of what? Compare in terms of their melting point. Right. So if you recall of such questions that you may have come across in your times when you were studying about ionic bonding, right? You may remember about this whole idea about, actually they mentioned that in sodium you have a 1 plus charge and chloride is a 1 minus charge. In magnesium you have a 2 plus charge, and oxide you have a 2 minus charge. And that's why we say that, because the charges here is 2 plus and 2 minus, whereas the charges here is 1 plus and 1 minus. Therefore, the ionic bond over here is actually stronger, and the melting point and boiling point over here is actually higher for the melting point and boiling point. So you may recall something like that you have come across. Actually, this slide over here actually helps to reinforce that whole concept by introducing you to this idea about charge as well as sizes of ions. So they use this equation here to represent what is the dependency between lattice energy as well as charge on ions. Basically, we say that lattice energy is proportionate to the charges of the cation and the anion, and also inversely proportionate to the radius of the cation and anion. So Q plus and Q minus represents the charges on the cations and anions. Essentially, we are looking at a case whereby the larger the charge, the stronger the attraction. Right, so this should be quite intuitive, I would say, and therefore your lattice energy, it will be even more exothermic. And then when we look at the denominator, right? So denominator, we look at this idea of radius, right? So the larger the radius, the weaker the attraction. Now, why so? Because if you think about it, if the ions are huge, right, the radius are big, that would mean that the attraction between the nucleus right, of one particular cation and the electron cloud of the other anion will not be as strong as what we expect, right? So the attraction will be weaker in that sense, right? Also, just want to clarify one mistake that I made on this slide itself, where I mentioned this is not about charge density, right? Apologies for that. Charge density is another concept that you look at it in the next few slides, right? So because of the formula that we're looking at over here. So essentially what we're trying to say is that lattice energy, we look at the charges of the ions and we look at the sizes of the ions, right? And based on that, we can deduce whether something have a high lattice energy or low lattice energy. So coming back to this example of NaCl and MgO, what I can conclude would then be that NaCl has a less exothermic lattice energy than MgO. Because if I compare the charges, I know that MgO, the charges here is actually way higher. And although you don't know yet, but these two, their ionic radius should be more or less pretty close to one another, right? So this is just for your info, right? So I think this is something that we can take away to understand about this whole idea of lattice energy. Okay, so Born-Haber cycle, I mentioned this before when we were learning about Here's law. I don't want to go into this again, but we're going to use this whole idea of Born-Haber cycle once more in this video, and we're going to bring in all the different energy values and see how do we then actually use that to build our entire Born-Haber cycle or energy level diagram together. So the other energy that I want to talk a lot about is ionization energy. Now, ionization energy is important because it helps us understand the energy that's required to remove one more of electrons from one more of gaseous atoms. So the removal of electrons is to form cations, right, which are our positive ions. So you have recalled in your process of learning about ionic bonding that metallic elements tend to form cations, right? So you can remove electrons from metallic elements and they form cations. So one good example would be, say from sodium, you become Na+, right? So that means there is an ionization process happening. It's always about removing that one electron. Likewise, from calcium, right? First, I can become a Ca+, then I can become a Ca2+. So what do I mean by that? This would mean that I'm actually looking at the first ionization in the first arrow, followed by a second ionization in the second arrow. For sodium's case, same thing, I'm looking at first ionization over here. Now, theoretically, you can keep doing ionization over and over again until you remove all the electrons from the atom or the ion in this case, right? So theoretically that is possible, but of course in terms of the energy that's involved, it will become more and more and it gets harder and harder, right? So we know that, for example, if someone comes up to you and say that, hey, have you seen before this ion called Na7+? You'll be thinking, how can this be possible, right? Because sodium group 1 valence electron, you should from Na7+. Now, but theoretically, I can go from Na to Na+ by using one ionization, then I go to Na2+ by using the second ionization, so on and so forth until I reach Na7+. So theoretically, yes, this is possible. But in terms of energy-wise, it is almost unlikely that you can go any further than Na+. And that's the reason why sodium only forms Na+, right? So this is something for you to take note of, right? And since we are talking about removing electrons, right? If you remove electrons, you need to add energy, is endothermic, right? Because you need to use energy to remove something away. So this is always going to be endothermic process. So you look at these notes, you realize that at the bottom of it, it shows you this idea of, hey, actually from Al, I can form Al+ first, then I form Al2+, then I form Al3+, and you can see the amount of energy is actually increasing as you go down, as you try to remove more and more electrons. Why is this increasing, right? It increases because it becomes harder to remove electron from a positive ion because electrons are negative, right? So if imagine now you have a positive ion now, which is Al+, and if you want to take out one more electron from it, then you can expect that it kind of electrostatic force of attraction to be much more significant, right? So this is something for you to think of. That's why the energy will get more and more. Okay, so electron affinity, which is the other energy change that I'm going to talk about. Electron affinity is the opposite case because now we are looking at the enthalpy change when one mole of electron is added to one more of gaseous atoms to form the gaseous ion. So a clear example here would be from chlorine, gaseous atom forming chloride, gaseous ion. Right? This will be one example of what we call first electron affinity. Okay, so of course, then theoretically, you can also say that, hey, then I want to add one more electron. Then I can form Cl2 minus gaseous, so on and so forth, right? But of course, using our current knowledge, which is still applicable over here, we know that it's impossible for chlorine to form Cl2 minus, so on and so forth, right? Because currently we learn that, oh, group 17, 7 valence electrons, you should need to add one more electron, right? So that is what we learned in O-level, but eventually you realize that why is it not possible? It's because the energy, right? It's impossible for you to keep adding electrons because the energy that's involved is so significant that it's not possible for it to take place. Okay, another example, let's say you have oxygen atom, right? You can go from this to O minus as an ion, then you go to O2 minus as an ion. So in this case, you have your first EA and then your second EA, right? So these are just some important concepts to understand about how it plays a part in helping us understand that actually whatever we learn now about ions, right? Actually, there's a meaning behind why energy is involved and what kind of charges it can form. Okay, so just take note that usually the first EA will be negative. Why? Because you are forming an attraction, right? So this is as good as saying that you are forming new attraction, just like forming bond. So formation of something that's new is always going to be exothermic, right? So I think this is quite standard. However, what gets a bit weird now is that the second and subsequent EA is almost always positive. Why is that the case? Because think about it, using oxygen as an example, so the first EA is when you have a neutral oxygen, you want to add in one electron, right? So the electron coming in, then it forms an attraction. So in this whole process, you get a O minus, right? So this is what it means for the first EA. For the second EA here, you have a O minus, and then you're trying to add in an electron, which is also a negative, to form a O2 minus. Now, when you're trying to add in this, you expect some repulsion. Why is there repulsion? Because the O is a negative ion and the electron is also negatively charged, right? So there will be some form of repulsion between the two, and then in order to overcome this attraction, overcome this repulsion, you need to involve energy being taken in, right? And therefore that's why it's usually going to be endothermic as a process. Okay, so that's your electron affinity in terms of the concept. Okay, so we're going to use an example here now to see how the bond paper cycle can help us to understand the formation of Na2O from its elements, and then use this to calculate the lattice energy of Na2O using this set of data. So likewise, they're actually expecting us to use the data booklet, right? But I'm not going to focus too much on the data booklet, but instead I'm going to use this as a chance to help us explore a bit about how can we apply the concept to help us understand about how lattice energy, ionization energy actually all come into place, right? So this question requires us to look at the formation of Na2O and figure out the lattice energy of Na2O. So I'm going to use a energy level diagram first, right? So remember about the elevator going up and down, so we understand what's going on. We know that in this question here, they want us to form Na2O from element, and then we want to know what's the lattice energy of Na2O. They did give us some values over here, so I'm going to use all these values to help us with our calculation, right? So we know that enthalpy change of formation is -414. So first and foremost, enthalpy change of formation would mean the amount of energy I need for the formation of 1 mole of that chemical, right? So in this case, this would be the enthalpy change of formation for Na2O, right? So how much energy do I need to form 1 mole of Na2O from its constituent elements under standard condition, right? So constituent elements will be sodium, and oxygen. The reason why I use half O2 is because I want to force myself to make sure it's actually 1 mole of Na2O only, right? Certainly something we mentioned about. Next, we're supposed to, the whole question is about finding about lattice energy, right? So what we can do now is that we can look at these chemicals here and ask ourselves, how can I form ions from them? So first and foremost, what I can do is that I can actually convert my sodium here, the 2 sets of sodium, into now a gaseous atom. So how do I convert sodium into gaseous atom? That's where I use this idea of lattice energy of atomization. The enthalpy change of atomization for sodium. Right? So I convert sodium into gaseous atoms. Similarly, the half O2, I can convert it into just an oxygen gas atom, right? And how do I do that? That's where I use my bond energy, right? So this will be half set of the O double bond O energy. So I imagine that I break the bond of the oxygen molecule and now with 1 oxygen atom coming out only. So from this then, I need to form my ions. So I look at my IE of sodium. Because I have 2 sets of sodium, I have to multiply by 2 times, and then I should end up with 2 sets of Na plus ions. I have the oxygen here. I will have 2 electrons that came out from this whole process, right? Next, I want to use my oxygen, and I want it to take in this electron. That's where I need to look at my electron affinity, right? So what could happen most likely is over here is that I will need to first add in my first EA of oxygen. So I add in the first electron inside. I should end up with 2 Na plus gas and then 1 O minus gas, but I still have 1 more electron over here. Right, the first EA is usually gonna be exothermic because attraction is formed, and therefore the energy will be as such. Then I have my second EA. Second EA is usually endothermic because energy is required to overcome the attraction. So let's say I reach here, then I will end up with 2 Na plus G plus O2 minus G. Right, so now the electron has been taken in by the oxygen ions already. So taken together, what this means is that from the gaseous ion all the way to form the compound, right, this is actually what I call my lattice energy, right? Because I look at the energy level and how it changes, right? So if you use a Hess law, what it teaches you over here is that this is like a loop, right? So the loop itself, the energy value must tally up, right? I'm not going to go into the details about the calculation because I think you can look at it in the next page over here in terms of how the values come in. Just want to use this as a chance to recap about Born-Haber cycle and Hess law, right? Remember, Hess law tells us that regardless of the pathway that the reaction takes, so long as the initial state and the final state are the same, right? Just like going from school to Bedok Reservoir, right? The overall energy change must remain the same, right? So this is an example of how you apply it, right? And then you should end up at this particular value. Right, so I think that's something I want to highlight to you as we are exploring this whole idea about lattice energy as well as IE and EA. So just want to emphasize a bit more, maybe perhaps about LE, right? So lattice energy, one important concept to take note of is that experimental and theoretical value can differ. Now, I've been talking about this experimental and theoretical value quite a while, and you'll realize that it's quite common for these two types of values to not tally up. And that is actually because when you look at the lattice energy of the chemical, right, it's usually because of the fact that the chemical is not a pure ionic compound, right? Because it is a bit new, okay, but when you look at theoretical lattice energy, we are looking at assuming that the compound is completely ionic. But you will grow to realize that actually not all ionic compounds are 100% ionic. Some ionic compounds, they still have ionic bonds. I'm not saying they don't have ionic bonds, but they actually have what we call covalent character. Alright, so allow me to explain a bit more about what do I mean by some ionic compounds have covalent character, and let's take a look at just a set of data over here to try to understand the concept about this whole idea of covalent character and what it means. So in this table itself, right, what they're trying to show you is that there's this set of things called experimental value in terms of the lattice energy, and also this set of value called the theoretical value. And you realize that more or less for sodium chloride, the value actually kind of checks out, right? Only a minor difference, but not something to be too worried about. And then we look at silver fluoride, right, AgF. We realize that the value between these two is okay, slightly different as compared to sodium chloride, but sodium chloride is like very, very close. Then you look at AgF, and then you look at AgI, silver iodide. And you realize that the difference here is almost about close to, let's say, maybe about 280. And over here, the difference is about maybe 140. This is a difference. So what you see over here is that, hey, there's actually a difference between the experimental value of silver fluoride as well as its theoretical value. And same for the case of silver iodide. And specifically, it's a bigger difference for the case of silver iodide. Right? And we're trying to see why is that the case. So how do you understand this idea about why sometimes the lattice energy is experimental and theoretical data actually doesn't tally? So remember, the concept that I'm going to explore over here is this idea about ionic compounds with covalent character. Right, so what exactly is this covalent character? Because covalent is not sharing, right? So when will this happen? This happens usually when there is a certain kind of concept called charge density, and also partly due to the electron cloud size of the anion. Right, so I'm going to use this as an example to see what's actually going on. What exactly am I trying to say over here? So let's try to visualize silver ion as well as my fluoride ion. And what do we mean by visualize? We visualize them as a cloud of electrons. So I think Mr. K already mentioned to you all that actually electrons exist in what we call principal quantum shell, orbitals, so on and so forth, right? So you have your s orbital, p orbital, so on and so forth. But to make things a bit simpler, I'm just going to use a circle to represent where the electron clouds are. So for silver, this entire pink area is where my electrons are. And for fluoride, this entire green area is where my electrons are. So these I call them, I'm just going to put a bit of a legend, this is called electron cloud. Okay, so this is where the electrons are for the both of them. So when you have ions, you have the bracket and the charge. This is what you already know in your ionic bonding dot and cross. So this is what happens here. So the case of silver fluoride is such. Okay, now let's take a look at the case for silver iodide. Right. So for the case of silver iodide, this is all you have is also I minus. There's not much of a diff. But you realize that this time around, my electron cloud is a lot bigger, right? Why is it bigger? So you recall that. So you recall that first, iodide has a larger ionic radius. Why? Because if you recall in your periodic table, right, as you go down the group, the size of the atom, or in this case, the ion will actually increase because they will have now more principal quantum shell, right? So the electron cloud is actually bigger in size. Now, why is this electron cloud important, and how does this help us to understand about covalent character? Okay, silver is silver ion over here is a cation, right? So these cations over here, what they can do is that they can actually attract electrons towards themselves, and this is what we call the distortion of electron cloud. So by distortion of electron cloud, what am I trying to say? What happens is that because of the ability of the cation to pull electrons towards itself, right, what will most likely happen is that for your iodide ion, the electron cloud will not be something that is so nicely confined within the iodide ion. Instead, there's a tendency for it to be dragged a bit closer towards the silver ion because of the ability of the silver ion to distort the electron cloud. And as a result, your iodide ion will have this kind of distorted electron cloud, and this is what we call an ionic bond with covalent character. Covalent character because it looks like the electrons are being shed, right? It's coming closer towards the silver ion to the extent that it's almost at the silver ion side. So when iodide ion has a larger ionic radius and hence a larger electron cloud, what this means is that the silver ion can cause a distortion of electron cloud of iodide, and this will actually form ionic bonds with covalent character. And that's the reason why we realize that the theoretical and experimental value for silver iodide, the lattice energy, is actually so much. There's actually so much difference because it is not a very pure, not a very purely ionic model. When you look at the silver iodide as an example of ionic compound, as compared to silver fluoride, as compared to sodium chloride, right? So you realize that for silver fluoride, it is also not as perfect as your sodium chloride, which means that this cloud is also slightly distorted towards the silver ion. So there is also that bit of covalent character, but because fluoride is to begin with already a smaller ion, which with a smaller electron cloud, is less likely to be distorted as significantly as the case of iodide. So this actually helps to explain why, when you look at this kind of two sets of values, right, realize that sometimes certain ionic compounds actually do not exhibit the kind of expected lattice energy that you would like to see, and that's because they're not really 100% ionic compound model kind of thing. Okay. Okay. The last few energy, I will just leave it to you to read through in more details. Basically, there's an energy of hydration, which means to dissolve. Hydrating means to dissolve. And there's also this enthalpy change of solution, right, which is the energy change where one mole of a solid is completely dissolved in an infinite volume of solvent. Basically, the whole dissolving process, there's also an energy change involved. Okay, and then the next few slides will show you how you actually can bring together this energy, enthalpy change of hydration, and enthalpy change of solution. So we use one example here to look at it. Let's say we look at this chemical called MX, like for example over here. So we know that in your ionic compound there's a lattice structure. So imagine there's M, there's X, there's M, there's X, and this thing just keep repeating over and over again. Right, so these are ionic lattice structure, if you recall. So imagine a lattice that goes on and on. Okay, sorry for the drawing. So this is a lattice structure. So what happens when you're dissolving an ionic compound? First, when you add into water, the kind of ionic bond that's between them, right, must be overcome. So you must break all these ionic bond, cutting across all the ions. Only when you do that, then can you separate out your respective M as well as your X ions, your M ion, and your X ion. Then they'll be moving around. So that is the whole idea of trying to dissolve something. And when that happens, what you're looking at is you're looking at negative lattice energy. Because lattice energy is to form, right? But now you're trying to split them back into their ions. Now they have not dissolved yet, you only split them up. So what do you do now? Now we try to hydrate them. What is hydration? Hydration means you look at the M ion and you actually surround it with a lot of water molecule. Now I'm using these 3 circles Mickey Mouse to show you what water molecule looks like, right? So imagine if your X ion over here, you also need some water molecules to be around it. Only when this happens, that is considered that they are dissolving, right? And to do so, you need to look at what? You need to look at the enthalpy change of hydration. That means you're trying to dissolve the ions, right? So what this means is that in this whole process, right, you need to first break the ionic bond, then you need to form the kind of hydration process that's happening. Then you can conclude that this whole process of dissolving has completed. Right? So dissolving, what does it mean? You need to first separate the ions, then you need to hydrate the ions. So that's a whole idea of dissolving. So this actually helps us to understand that, hey, actually there is a way to look at the energy value also, because this whole process of dissolving is represented by the formula, the enthalpy of change of solution. So what is enthalpy change of solution equivalent to? Is equivalent to, first, minus away the Le, that means break all the ionic bonds. Then add up the enthalpy change of hydration energy, depending on how much it is, whether it's exo or endo. Then the summation of this thing, just like Hess law, right, will be equivalent to your whole idea of dissolving something. So I think this is the key concept that we are trying to emphasize over here in this particular slide, right, and this drawing that I'm trying to show you what it actually means. Okay, so I hope this is a bit clear.